Let's take a look at another example of a situation where I may want to use a linear function as my u in my substitution. Here we want to integrate secant of 6x times tangent of 6x with respect to x. We want to find the class of antiderivatives of secant 6x times tangent 6x. We're going to do this the long way to begin with. We let u equals 6x. That means the du with respect to x, derivative of u with respect to x, is just the constant 6, which means du is equal to 6 times dx, or the way I'm going to look at it is 1/6 du can replace our dx. In this situation, there's actually nothing to rewrite or redo in terms of how I'm going to be doing my substitution. Each 6x is replaced with a u. The dx is replaced with a 1/6 du. I'm going to put the 1/6 out front. In fact, I'm going to pull the 1/6 out in front of my entire integration symbol. Secant tangent, we've went over the antiderivative of secant tangent before. I hope you remember that the antiderivative of secant tangent is secant. In this case, since we're dealing with the variable of u, we get 1/6 times secant of u plus c. Obviously, the u there came from 6x. So our final answer would be 1/6 times secant of 6x plus c. Again, that would be my final answer. Notice once again, having a linear piece that I created and made my u essentially just meant that I think of secant tangent, the antiderivative of secant tangent is going to be secant of my argument, which in this case is 6x. And because my argument is a linear piece with a coefficient of 6, I need to divide by 1/6 out front. So linear pieces are really nice in that when I substitute out with linear pieces, a lot of times I just end up dividing by that coefficient of x out front. We saw that happen in our earlier problem where we just ended up dividing by 4 out front and taking natural log of this argument. In this case, 4x minus 9. We ended up dividing by 4. When we had secant 6x, we ended up dividing by 6. Knowing that, I want you to try the next problem. This is not a you-do problem, but I would like you to just pause real quick and think about what the integration of e to the 8x could turn out to be if the linear scenario held up in this case. Think through. I'm going to give you a few seconds to think through what the class of antiderivatives could be for e to the 8x. I hope you at least thought through that. If you don't, if you want to write something down and think through more, obviously push pause. But I'm going to keep pressing forward here. We want to integrate e to the 8x. If the pattern were to hold true, the u would be my exponent, and I would integrate e to the u and just get an e to the u, or e to the 8x in this case. Because my coefficient of x is 8, I'm going to get a 1/8 out front. Once we realize that that is what's happening with the linear u's, my process and my thinking can just automatically go like that. By the way, we can figure out this rule as well. Let's take e to the ax, where a is any number. Using substitution, we would have set u equal ax, and then du with respect to x would have just been the constant of a. I can rewrite that as a differentials problem. The du would be equal to a times dx, or 1 over the number a times du would equal dx. When I would have done my substitution problem, the e to the ax would have turned into an e to the u. The dx would have turned into 1 over a times du. I'm going to write the 1 over a out front. Notice what this is. This integration is going to be 1 over a multiplied times e to the u plus a constant. And then obviously my u was a times x. Many times, once we've seen this over and over and over, you will just be able to say that when you integrate e to a linear power, you end up with 1 over a e to that linear power plus c. The same is going to be true for a lot of functions. A lot of my trig functions are going to work that way as well. Let me write at least a couple of those down. If I want to integrate cosine of, if I want to integrate cosine of ax with respect to x, what's going to happen is my u is going to be the ax, and we're going to end up going 1 over a. The antiderivative of cosine is a sine, so we just take sine of ax plus c. Similarly, if you're going to integrate sine of ax with respect to x, you could do 1 over a. The antiderivative of sine is negative cosine. Let me write the negative out in front of the 1 over a of ax plus c. You can also do it with natural logs. We've seen this one earlier, or we've seen at least one example of this earlier. Let's take ax plus b. By the way, I've just been doing ax. You can do ax plus b on all of these. If you do ax plus b over there, you have to do ax plus b over here, ax plus b over here. But you always get just dividing by 1 over a. In this case, we're going to take natural log of ax plus b plus a constant, but we're going to have to divide by 1 over a. Or I should say multiply by 1 over a is the same thing as dividing by a. So with linear arguments, substitution works out really, really nicely, where I can just take the antiderivative of the linear argument and then divide by a, or multiply times 1 over a being the coefficient of x. A lot of this is going to come up a lot if you go into Calc 2. If you go into Calc 2, you're going to see this property a lot. You're going to see this property quite a bit. You're going to see this property a lot. That's why I wanted to point it out now.